Let's talk about the integral tests for convergence. When we cannot evaluate an improper integral directly, we try to determine whether it converges or diverges. If the integral diverges, we are done. If it converges, we can use numerical methods to approximate its value. The principal tests for convergence or divergence are the direct comparison test and the limit comparison test for integrals. You'll often hear me abbreviate the direct comparison test for integrals to DCTI, which says if 0 is less than or equal to f of x, which is less than or equal to g of x on the interval from a to infinity, where a is a real number, then 1, if the integral from a to infinity of g of x dx converges, then so does the integral from a to infinity of f of x dx. The second item says if the integral from a to infinity of f of x dx diverges, then so does the integral from a to infinity of g of x dx. Why does this make sense? Well, 1, if the area under the curve of g of x is finite and f of x is bounded above by g of x and below by 0, then the area under the curve of f of x must be less than or equal to the area under the curve of g of x. A positive number less than a finite number is also a finite number. 2, if the area under the curve of f of x is infinite and g of x is bounded below by f of x, then the area under the curve of g of x must be greater than or equal to the area under the curve of f of x. Since there's no finite number greater than infinity, the area under g of x must also be infinite. Here's the big idea broken down into 4 cases. We want to know something about a given function. We know or can easily find information about a friendly function that we create. So again here, from our picture, we have our function g of x, which is greater than or equal to our function f of x. Now here are our 4 cases. Let's move over to this second case here, and we'll come back to the first case. So suppose we know that the integral from a to infinity of g of x dx converges. Because the area under g of x is finite, that's what it means by converges, and because f of x is bounded above by g of x, this has to imply, and our conclusion has to be, that the integral from a to infinity of f of x dx also converges. Let's go ahead and move on to the next case. Suppose that the integral from a to infinity of f of x dx diverges, so that means that the area under f of x here is infinite. Now, because the area under g of x is more than that, it also has to be infinite, so that means that the integral from a to infinity of g of x dx also diverges. Now, let's move on to the next case. Suppose that the integral from a to infinity of g of x dx diverges. That means that the area under g of x is infinite. However, f of x is smaller than that, so it could either be infinite or finite, which means that in this scenario, we can't really come to a conclusion. In other words, this is inconclusive. Now, the first case which we skipped over says that the integral from a to infinity of f of x dx converges. So in this instance, the area under f of x is a finite number, but g of x's area underneath the curve is some number that's larger than that, and that number could be finite or it could also be infinite. So in this case, we also are dealing with the scenario of being inconclusive. Example 6 says determine if the integral from 2 to infinity of cosine squared x over x squared dx is convergent or divergent using the direct comparison test for integrals. So what I'm going to do here is I'm going to start off by talking about cosine of x. And I know from trigonometry that the range for cosine is all numbers between -1 and +1. So in other words, cosine of x has to be less than or equal to 1. Now, if I square a number that is less than or equal to 1, then that number squared also has to be less than or equal to 1, assuming that the number is greater than or equal to -1, which in this case cosine is. So we have this implication here. Now, and notice that we're integrating on the interval from 2 to infinity. So in other words, x exists in the interval from 2 to infinity. So this inequality implies if I take both of those values, then if I divide by x squared is going to be a positive number, so my inequality symbol is not going to change. So this is still going to be a true statement. Now, what I can do is I can take the integral of both sides from 2 to infinity. So let's start off by integrating this side. And by this side, I mean the right-hand side, because we don't have the tools to integrate cosine squared x over x squared in this class as of right now. So this integral on the right-hand side, we know that this converges by the p-test because p is greater than 1. So our basically larger function converges, and so therefore by the direct comparison test for integrals, the integral from 2 to infinity of cosine squared x over x squared dx must also converge. So there's our final answer, and if you're taking my class, it's very important that you name drop these theorems and things. So you gotta name drop the p-test, and you gotta name drop the direct comparison test for integrals to help you come to your conclusion about whether the integral converges or diverges. Example 7 says, determine if the integral from 3 to infinity of 1 over x minus e to the negative x dx is convergent or divergent using the direct comparison test for integrals. So let's recognize that the x values that we're looking at are on the interval from 3 to infinity. And I want to start off by thinking about just the value of x. And we're able to make the statement that x is greater than or equal to x minus e to the negative x. And e to the negative x on the interval from 3 to infinity is going to be a positive number. So if I'm starting off with the same number and then subtracting off some positive number, then this is definitely going to be a true statement that x is greater than or equal to x minus e to the negative x, which implies that if I were to take the reciprocal of both of these, then the inequality sign would flip or change direction. And so if you don't understand that concept, here 3 is less than 4, but if I were to take the reciprocal of both of these, if I were to take 1/3 and 1/4, 1/3 is greater than 1/4. And there's a really interesting and somewhat famous case study. McDonald's sells a hamburger called the Quarter Pounder, and one of its competitors started selling a burger called the Third Pounder, but Americans wouldn't buy it because the average American thought that a quarter pound was greater than a third pound, which is not true. So hopefully you're able to reconcile your fractions. So coming back to our inequality, if I take the reciprocal of both of these, I'm going to have that 1 over x is less than or equal to 1 over x minus e to the negative x. And what we can do now is we can take the integrals of both of these, And we know something about the left-hand integral. This diverges by the p-test because p, our power, is equal to 1 here. So since our smaller function basically, so if we went back to our picture, we could basically call 1 over x f of x, and then we'd call this thing g of x, where g of x is greater than or equal to f of x. So since our smaller function diverges, then the larger function also has to diverge. So coming back down here, we can say therefore, by the direct comparison test for integrals, the integral from 3 to infinity of 1 over x minus e to the negative x dx must also diverge. And there's our answer.